Good morning, everybody, and welcome again for this seminar from the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Julia Ereza. She will talk about high-fidelity Sky Moc for DESI galaxies in the LCDM cosmology. Julia is from Seville, here in Andalusia, in Granada, and she studied a double degree in physics and materials in engineering. After finishing the degree, she studied at the University Autónoma de Madrid, the Master in Theoretical Physics, that is taught in collaboration with the Institute of Theoretical Physics from CSIC. In particular, the specialization in astrophysics and physics of the cosmos. She's currently in her second year of the PhD here at the Instituto de Astrofísica de Andalucía on the extragalactic astrophysics department. Her work consists of trying to understand the formation of the universe on a large scale and the formation and evolution of dark matter halos, the galaxy halo connection, the nature of dark matter and dark energy. To do so, she made use of cosmological simulations. So she recently participated in the data release of Uchuu, the largest and most realistic cosmological simulation today. Uchuu, which has been developed in an international collaboration, has been carried out on the Japanese supercomputer ATERUI II, the most powerful supercomputer in the world dedicated to astronomy. And thanks to the Centro de Supercomputación de Galicia, is available to everyone. And Julia also is an active member of DESI, which will provide the next major galaxy catalog, replacing the current Sloan catalog. So thank you very much, Julia, for this talk. And the floor is yours.
Thank you. Okay, so, well, I'm gonna start. As you can see in the title, I'm gonna describe how we have constructed a high-fidelity Sky Moc of DESI galaxies in the LCDM cosmology. So I have done this work in collaboration with some people of data that you can see mentioned here, also Francisco Prada, who also work in the institute. Okay, well, let's start. Sorry. Okay, here is the outline of my talk. First, I'm gonna start describing what we call a high-fidelity Sky Moc. The next step is how to build one. Also, I'm going to show the results between our Sky Moc that we have constructed with the Uchuu simulation compared with the Bose CMAS data, and also the future plans that we have with DESI. So the first thing to notice is that you may see this Bose CMAS data, and maybe you don't know what it is because I didn't even mention it in the title, but I'm going to show the results using those data. So I'm going to briefly describe this aspect. The Bose CMAS North data refers to the Baryonic Oscillation Spectroscopy Survey, which is designed to measure the scale of the Baryonic Oscillation, the so-called BAO, in the clustering of luminous red galaxies. So Bose have two distinct samples, the low CMAS and the CMAS. The CMAS covers a redshift between 0.43 and 0.75. This is the range, the redshift range that we are going to use to compare our Sky Moc and the sample. And the N just refers to the north hemisphere. So now that this is clear, I'm going to start with the first point, which is what is a Sky Moc. So a Sky Moc is a sky catalog built with cosmological simulation. A sky catalog is just an observed sample, a sample that has been observed by a certain survey. For example, here you can see these two slides of the plot are the real observed data. while these two ones are the Sky Moc that have been produced using the Millennium simulation to replicate those observed data. So this is essentially a Sky Moc. And the most important question maybe is what it is for. So they have a lot of applications. Among them, we can obtain accurate constraints of the cosmological parameters, thus checking different cosmological models, check if they describe correctly the formation of the structures in the history of the universe. Also provide covariance errors to the observed cosmology proofs, for example, for the DEO. Better understanding of the survey systematics, understanding the nature of dark energy and dark matter, and so far many more applications, for example, testing the galaxy formation and galaxy evolution models. But essentially what a Sky Moc is for us is our laboratories, and we cannot make any experiment in any laboratory. We have to use our Sky Moc as a laboratory. So the next step is how to build one. And I have said Sky Moc is a sky catalog built with cosmological simulations. So maybe you work in this field and you are familiar with what cosmological simulations are, but maybe you are not. So I'm gonna briefly describe them to put the context. So, well, this is a picture that for sure everybody knows. Here we can see the evolution of the history of the universe from the Big Bang to the present day, how the particles goes from the thermal bath to the galaxies that we observe today. So one of the main objectives of the cosmology is understand how these structures were formed and the laws that govern that gravitational bonding that forms the structures that we see today. So due to the non-linearity of all these processes, analytical approach is very difficult to achieve. So that's where we introduce the cosmological simulations. There are many different, well, a lot of kind of cosmological simulations, but we can make a main distinction, which is the hydrodynamical simulations and the Embody simulations. The hydrodynamical simulations include dark matter and also baryonic matter, which implies that we have to introduce not only the gravitational force, but also the electromagnetic and nuclear forces. While the Embody simulations only include dark matter particles, so we only have to include a gravitational force. So maybe you can ask, okay, so why will anybody want to do an Embody simulation while you can do a hydrodynamical simulation that is a much more realistic simulation since it includes all kinds of particles and all kinds of forces? And the answer is, well, space and time, because doing an hydrodynamical simulation is very computational expensive. It takes a lot of time, a lot of computational hour, and in our field, of course, it depends of the field. But here in cosmology, we need simulations that replicate large volumes and also large scale times. So we need very big simulations. So doing an hydrodynamical simulation with these characteristics is impossible for us. That's why we use Embody simulations that only include dark matter. Also, at these scales, the dark matter, the baryon, we don't need to know how a particular galaxy were formed. We just need to know the distribution of matter at larger scales. And we know that the baryon matter follows dark matter. So by simulating that matter, we are okay in our field. So, well, we are going to use Embody simulations. They are very easy to create. You just create a cube in your computer of size L with M particles and dark matter particles within the cube, and you distribute them according to the matter power spectrum that you obtain from the CMB, the cosmic microwave background, and you just introduce your cosmological framework, which could be lambda CDM, modified gravity, early dark energy models. You introduce also the gravitational laws according to that cosmological framework, and just press play. You just let the gravity do its job, and what you finally obtain are different snapshots from the simulation, which means that you can know the exact position of each of the dark matter particles that you have included in your cube at different redshift, which in cosmology, redshift means space and time. The higher the redshift of the box, the farther you are looking at, and also the earlier in the lifetime of the universe. Otherwise, redshift 0 is today, which is the nearest part of the sky to us, and also the latest time in the history of the universe. So, well, the Embody simulation that I'm going to use to produce our Sky Moc is the Uchuu simulation that René has introduced before. I'm going to briefly explain it. This is a 2.1 trillion dark matter only Embody simulations that use Planck 15 cosmology. You can see here the cosmological parameters of this Planck 15 survey. Uchuu simulation can resolve halos and subhalos, which subhalos are just halos within halos. Well, we have a lot of random sample particles, merger trees, galaxies, and lensing maps are available for everyone that want to access them, thanks to FESCA, the Centro de Supercomputación de Galicia. Well, this is just a technical introduction of Uchuu. So, one of the main aspects that our Sky Moc has to have is that it has to reproduce the galaxy clustering evolution with redshift. That means that the galaxies do not cluster the same way today that they do 2 billion years ago. So we need to reproduce this different clustering with redshift in our simulation. To do that, what we do is using different boxes, different redshift from the simulation that we have do. We use boxes that cover a certain redshift range and put them in for example, the lowest box, the lowest redshift box will be the nearest one in our Sky Moc, while the one that have the highest redshift will be the farther one. So we are going to use different boxes of different redshift just to reproduce the galaxy clustering evolution. So let's start with the methodology itself. So the first thing I have to say, Uchuu is an Embody simulation, which only use dark matter particles. So at the end, we only have dark matter halos. But if we want to reproduce a galaxy sample, we have to include galaxies in our simulation. So the first step is add galaxies to the halos and subhalos of each of the Uchuu books that we have used. We are going to do this using the subhalo mass matching method and using the observed stellar mass function. I'm going to describe this word. Okay, so this is, for example, an output of our simulation. We have the ED of each of the halos. We don't care if they are halos or subhalos, just all the halos that we have in our simulation. We rank them by VPIC, which is a proxy of the mass of each of the halos. And we rank them from the highest to the lowest VPIC. And this way, we don't care if they are a halo or a subhalo. And by using the stellar mass function, which gives us the number density of galaxies that have a certain mass. Here you can see the different masses of the galaxy in solar masses. This is just the number density of galaxies. By following these statistics, we can correlate the VPIC with the stellar mass of each of the galaxies that are going to be in each of the halos of subhalos of Uchuu. That's how we introduce the galaxies. In fact, these stellar mass functions are the ones that we have obtained from the real Bose-CMASS sample. So this is the real distribution of galaxies that we see in the sample, and this is the distribution of galaxies that we are using to introduce galaxies in our simulation, in our Uchuu simulation. The next step is join these boxes to reproduce the galaxy clustering. So in each of the boxes of Uchuu, which have a different redshift, each of them, we introduce the stellar mass function and correspond to that redshift range. Thus, we Doing this process, we replicate in each of the boxes the galaxy distribution that the sample, the survey is observing in the universe in each of the redshift. So that's how we replicate the galaxy clustering. When we have all the independent boxes with the galaxies added, we just join them to replicate the clustering evolution. Once we have all the boxes together, that we have already our galaxies that reproduce the redshift evolution in the clustering, we now have to cut our boxes to the sample that is observed by the telescope. So this is the sky area observed in the BOSC-CMAS North sample. And this is our Sky Moc once we have cut it to the real observed data. For example, this lack of data is maybe because a bright star that do not allow us to see any galaxy in that area, maybe some fibers that are broken and this precise area could not be observed. These kind of things are the ones that we replicate when we apply the mask to our Sky Moc. The next step is fix the number density following the observed radial selection function. Okay, so this curve just tells us the number of galaxies that we have at a given redshift. So since we have each of the boxes with a fixed number of galaxies and we have joined them, we have to smooth that joint of boxes. So the green line is the number density that we have just with the boxes joined, and we have to smooth it to the real number density function, which is the black one. So just a simple method that smooth the joint of each of the boxes to have a smooth radial selection function of galaxies. The next step is add the observational systematics to our Sky Moc, which could be the completeness of each of the area observed in the sky, the fiber collision, also bright galaxies, bright star, I have said before. So we, by each of the different areas that we have observed, that have been observed in the BOSC-CMAS survey, we replicate that density of galaxies in our Sky Moc. So here you can see, this is the sky area observed, the real sample, and this is our Sky Moc. This is the normalized density of galaxies for each of the areas that have been observed. So that's all. Yeah, what we finally have is a Sky Moc that reproduces the galaxy clustering evolution size. We have joined different boxes of different redshift, and also that replicate the observation, the observed area, all the systematics, all the radial selection function. So we have we already have a Sky Moc. Now the next step is check if our methodology and our cosmological framework that we have assumed, that is LCDM, and in particular the Planck 15 cosmological parameters, we have to check if all these work agree with the observed data, or maybe if there is something wrong. So to check the accuracy of our Sky Moc to replicate the observed data, we are going to use the statistic tool that is called the 2-point correlation function. We just measure the excess probability above what is expected from a random distribution of finding a galaxy at a separation r from another galaxy, which in other words means given a galaxy at a certain position, with the 2-point correlation function, we can know what is the probability of finding another galaxy at a distance r from the first one. So that's just the 2-point correlation function. But first, there is a main aspect that we have ignored at the moment, which are the error bars. What are the error bars in our case? So since we are not observing the full picture, either in our Sky Moc or in the real sample, we are just observing a small area of the full sky, a small redshift range of the full history of the universe, we need to run the simulation several times in order to have access to statistics that will help us to estimate the errors. So we cannot run Uchuu 1,000 times. That's impossible because running Uchuu one time already took us 1 year, so we cannot run in 1,000 times. It is too big, have too many particles, it have too high resolution to run it several times. So we cannot use Uchuu to estimate the errors. So what we do is use what is called the GLAM-Uchuu simulations, which are simulations that have the same cosmology as Uchuu. That's why they call Uchuu. And the GLAMs is because they are also embodied dark matter simulation, but they replicate a lower volume. There is only 1 gigaparsec box, while the Uchuu box is 2 gigaparsec box. It has a lower number of particles. It has also a lower resolution. We still have enough resolution to reproduce a Sky Moc that allows us to compare it with the data, but it's also low enough to allow us to run it several times, in fact, 1,000 times. So we have run GLAM-Uchuu simulation 1,000 times. So now we can compute the statistic that will give us the errors of our Sky Moc. So we have again produced 1,000 GLAM-Uchuu Sky Moc. The methodology to construct the Sky Mocs for GLAM-Uchuu is the same as Uchuu, just with one change. As I have said, the GLAM-Uchuu simulations has a lower resolution, which means that GLAM-Uchuu is not able to resolve subhalos, only halos. While Uchuu resolves halos and subhalos, GLAM only resolves halos. So, as in Uchuu, we use the subhalo banda smashing method to introduce galaxies in halos and subhalos. That's something that we cannot do in GLAM because we do not have subhalos. So we need to use another methodology, which is the halo occupancy distribution. So to compute the HOD, we use the Uchuu Sky Moc. This is just the HOD gives us the number of galaxies that are in a halo of certain mass. For example, in a halo of 10 to the 13 solar masses, we have 10 to the minus 1 satellite galaxies, which are galaxies that are in subhalos within that halo, and also almost 1 central galaxy. So using these statistics, we can introduce satellite and central galaxies in GLAM, even though that GLAM do not resolve subhalos, just halos. So that's how introduce galaxies in GLAM. The rest of the process, the applying the mask, the radial selection function, the systematics is the same in GLAM-Uchuu as it is in Uchuu. So once we have our 1,000 GLAM-Uchuu Sky Mocs, we use them to compute the variance of each of the elements of the 2-point correlation function vector respect to their means. Thus allows us to quantify the errors of our statistics. So let's start with the results. Let's check the accuracy of our Uchuu Sky Mocs in its job to replicate the observed data, which is the BOSS-CMAS North data. Okay, so here you can see the monopole, which is the 2-point correlation function once you compute it in redshift space. Redshift space is just the position of the galaxies in sky coordinates, also taking into account the peculiar velocity of each of the galaxies. So maybe the galaxy can blue shift or redshift depending on its velocity along the line of sight of the observation. So here you can see again the monopole of the 2-point correlation function in redshift space. This bump is the Bayo we expected. You can see there, well, this is the same plot but in a smaller scale and in logarithmic binning. So here you can see that Uchuu, which is the pink line, and CMAS, which are the black dots, they are both in green, in great agreement. At this point, we expect this disagreement because, as I have said, we are observing a reduced area of the sky. So the BOSS-CMAS sample is not big enough, not wide enough to have a good statistic at the Bayo scale. So from this point to more large distance, this difference is due to the fact that we do not have enough data to have an accurate measurement of the two-point correlation function at this scale. So this disagreement is something that we expect. So here you can see the quadrupole and the hexadecapole, which are the anisotropic parts of that two-point correlation function computed in redshift space. These two anisotropic parts are more affected at the blue shift and redshift of the galaxies due to their peculiar velocities. So, well, even though we have still a very good agreement, again, all this noise is due to the reduced area. The small area that we are saying takes a more important, takes more relevance here in the anisotropic part of the two-point correlation function. So, well, this disagreement, we expect this disagreement, even though there are still even good agreement at a smaller scale. Our Sky Moc reproduced the curve of the data very faithfully. So this is a very good result. Here you can see the anisotropic correlation function. This two-point correlation function is computed along two beginnings, one perpendicular to the line of sign and one parallel to the line of sign. So this is the real observed data, and this is our Sky Moc. As you can see, they both have the same shape. We have this squashing effect, which is due to the galaxies falling inward over density in a linear regime, while this finger of God effect, which is due to non-linear effects of the movement of the galaxies. So, well, this is something that we expect. This is something that we are able to reproduce in our Sky Moc. So we are, again, in very good agreement with the observed data. So all these results not tell us that, first, our methodology is correct. We are able to reproduce the observed sample, but maybe the most important part is that the cosmological framework that we have assumed while computing Uchuu and also Planck Uchuu simulation, which is the LCDM cosmology, and in particular the Planck 15 cosmological parameters, are able to explain the formation of structures in the universe, at least within the error bar that we have at the moment. So we can assume that the LCDM model as a correct model to describe the evolution of the universe at this from the Big Bang till today. So, well, once we have seen that the LCDM model is a correct model to describe the formation of a structure and that our methodology is correct, I'm going to describe the future plans that we have with DESI. So, as you may know, DESI is the next major galaxy survey that will substitute the actual Sloan digital sky survey. Is international collaboration with more than 74 participant institutions where the AIA takes part. We are members of the collaboration. So, well, DESI, it will measure the spectra of more than 30 million galaxies and quasars, covering more than 14,000 square degrees from redshift 0 to 4 in over 5 years. Is mounted in the 4-meter Mayal telescope at the Kitt Peak National Observatory. Well, the main point of DESI is its novel design. It's composed of a roundish focal plane of around 1 meter of diameter, composed of 10 petals. It has a total of 5,000 robotic positioners. It's holding a fiber optic cable. We have 500 robotic positioner for each of the panels of the focal plane. So we are able to repositioning the 5,000 fibers in less than 2 minutes. And also the position of each fiber is better than 50 millimeters. It has also 10 spectrographs that cover 3 bands, the blue, the visible, and the near infrared, that covers from 360 to 1020 nanometers. So, well, DESI will cover a lot of tracers, in particular 5 target classes: the Lyman alpha forest tracers, emission line galaxies, luminous red galaxies, bright galaxies. So we expect to observe 5 target classes, more than 40 million redshift during the 5 year of observational the observational plan that we have with DESI. Well, after some delay due to COVID, we are now taking data that is going to be in the DESI main survey. We are in time, even though the COVID delay, and at the moment we already have observed more data than the actual Sloan survey. So, and we expect to observe even more. So, yeah, we're in a very good point. There is still not public data. We are still waiting for an internal data release. They are still working on the systematics and all that stuff that is very difficult to approach. So, well, till we wait for the internal data release, we can make some predictions using our simulations. For example, using the GLAM T-MIL no Veo, which is a GLAM simulation that uses the Planck Millennium Simulation cosmology, and we have one with Veo and without Veo. These 2 simulations will allow us to determine the statistical significance of the biodetection that we expect in the DESI main survey. So, well, I have said we are still waiting for the internal data release of DESI. We still have not any official data release. They are still working on the systematics. But once we have an internal data release, we are going to produce the Sky Moc for using also the Uchuu simulation. We are to produce it the same way I have shown here with the both CMAS data. And well, we expect to have a very better agreement between our Sky Moc and the data. So the sample will be bigger than the one that was CMAS. So, well, once the data release is done, we will be there with our Sky Moc to test the accuracy of our methodology and also the accuracy of the LCDM model in its job to explain the evolution, the structure formation in the history of the universe. So, well, that's all. Sorry, Renee, I was shorter than I expected. So thank you everyone for your attention. And maybe if you have any questions, you can ask whatever you need. Sorry, Renee.
Thank you very much, Julia. Very nice work. Okay, and now the talk is open for questions. Please raise your hand. So, Julia, just for breaking the ice, what is your specific work on your thesis using this data?
Well, I have already, well, my job is constructed the full LICON, and also, well, we have different, I can show you some extra slides. So here you can see here. Okay, this is the GLAM simulations. We already have GLAM simulations for different cosmologies for using Abacus cosmology, which includes massive neutrinos, the Uchuu cosmology, early dark energy cosmology, also modified gravity. So our plan is to test those different cosmologies with the data to maybe rule out some cosmology models or maybe check the accuracy in describing the structure formation of galaxies along the story of the universe. So
as I understand, the idea is to change any parameters, to change the cosmology and check with the simulation, right?
Yeah, exactly. We create Sky Mocs that replicate the observed sample. Once we have an internal data release in DESI, we can use our simulations to replicate that observations. Then, using the different cosmologies, we can see how well each of the cosmologies reproduce the observed data. Right. So we can maybe I don't know if rule out, but see that maybe something is not totally correct. Maybe we can do that using the different cosmologies. Yeah.
Right. Thank you. Rosa, please.
Hi, Julia.
Hi.
Very nice work. So
Thank you.
congratulations. I was lost at the beginning because what I understood that is that you every peak halo you assign it an stellar mass which is related with the stellar mass function. But for that, you had to assume a ratio between the mass halo and the galaxy stellar mass. Sorry, let me because
Sure.
I was confused at the beginning, and later you are also describing the halo occupancy density. So that means that for every halo you had assumed that could be more than one galaxy inside of it. So I was, maybe you want to elaborate more this comment because
okay, well, we in Uchuu that we can resolve halos and subhalos, we used it subhalo bandas matching method to introduce galaxies, which just means we have our data, which we have an identifying ED for an identifying number for each of the halos and subhalos that we have in Uchuu. Each of them has its peculiar mass, its peculiar V peak, and we rank them by V peak, which is a proxy of its mass. And at a stellar mass, we correlate the number density of V peak with the number density of galaxies by its stellar mass. So we assign for each of the halos and subhalos of Uchuu a galaxy. So the galaxies that are in a subhalo are called satellite galaxies, and the galaxies that are in a halo, in a distinct halo, are called central galaxies. So once we have galaxies in each of the Uchuu halos and subhalos, we can compute the number of satellites, central galaxies that we have in each of the distinct halos of Uchuu. I don't know. I mean, in Uchuu you have a halo with several subhalos inside. The halo itself have a central galaxy, but also each of the subhalos that are in the halo have each of them a galaxy also. So you can compute for this halo, you have one central galaxy and n satellite galaxies. And these halos have X mass. So you compute that statistics, go to GLAM and see, okay, I have this halo which have this mass. So according to Uchuu, I know that it have one central galaxy and n satellite galaxies. That's how we work, because we can use the subhalos of Uchuu to introduce a galaxy, a satellite galaxy, but we do not have subhalos in GLAM. So we have to use that statistic, knowing that a distinct halo have a certain mass, it will probably have n satellite galaxies that will be in subhalos that we cannot see in GLAM, but they will be there. I don't know if I have explained myself.
No, that is something that I missed, is that to go to the mass halo, to the stellar mass of the galaxy, you have to assume that there is a ratio between the mass halo and the galaxy stellar mass.
Yeah, exactly. Yeah.
This is the point.
Yeah, see, exactly. We use we actually do not use the V-peak. We use V-peak scattered. We add a bias in the V-peak to correlate the number density of V-peak with the number density of galaxies. So we correlate this stellar mass function with the number density of V-peak. So yeah, we assign one by one, but not with V-peak, but with V-peak scattered. But yeah, we assume there is a relation between the two. Yeah.
Okay, thank you.
Thank you, Rosa. Any other question for Julia? Okay. Seeing none. Thank you very much, Julia, for this talk.
Thank you.
The talk will be available in the IAA communication channel soon. Thank you for the talk.
Thank you.
Okay, I stop recording. So we are now off.